Hey guys, how's it going? Remington here, and today I have an educational video for you guys. Now this was supposed to be a Tech Tuesday video, but I got a bit busy last night, so I'm going to have to upload it today instead. Sorry for the wait. Anyway, I'm starting a new program on my channel about electronics and how to work with them and create amazing things. So this will hopefully go for a while, so if anyone is interested in seeing more of these videos and you aren't subscribed, I suggest that you hit the subscribe button. Anyway, we're going to be exploring the very surface of the vast realm of electronics, so let's get started. Before we begin developing any amazing electronics, we first have to ask ourselves, what is electricity? To find the answer to this, we have to look at the atomic level. Many of you will know that this is a diagram of an atom. It's made up of three elementary particles: the nucleus in the center, which is made up of protons and neutrons, and then their orbiting electrons. Each electron has one negative charge, each proton has one positive charge, and each neutron has one neutral charge. So what happens if we take a proton and an electron and put them together? So the proton has a positive charge, hence it's labeled P+. The electron has one negative charge. So if we let go of them, let's see what happens. It looks like they're attracted to each other. When we let them go, the proton and electron stuck together. So let's set up another experiment. I've taken two electrons, each with a negative charge, and placed them right next to each other. Let's let them go and see what happens. It looks like these two repel each other. From this we can conclude that opposing charges will attract one another and like charges will repel each other. So let's do another experiment here. I have a table set up with 6 electrons on one side and 2 on the other. They are divided by a thin membrane that electrons can pass through with ease. In this experiment, we'll see a natural occurrence called diffusion or equilibrium. You can see that the electrons have balanced themselves out across the membrane, 4 on the left and 4 on the right. This is because it is nature's natural state to balance things out. As the electrons balance themselves, they are moving. This movement is called a flow and is very important to understanding electronics. So let's set up our first circuit ever. All we have is a battery right now. However, you can see that on the negative end of the battery, there are 100 electrons, and on the positive end, there are 0. In reality, these numbers are very different. There are millions upon billions of ionized electrons in the anode, which is the negative end of the battery, and there are also just as many electrons in the cathode, in the positive end. The only difference is that the anode holds anions and the cathode holds cations. We don't need to get into that stuff now, that's all chemistry. However, we might get into some of that stuff later if you guys are interested. So we can see there's an obvious difference in the amount of electrons in the anode and the cathode. So nature wants to balance it out. However, since the anode and cathode aren't touching, electrons can't be transferred between them. So let's attach a wire to both of them. A wire is made up of a conductive material, unlike the middle of the battery. Conductive materials will allow electricity to flow through them. However, non-conductive materials, or insulators, will not. Now that we've connected this wire, we see that the electrons are beginning to flow from the anode to the cathode, slowly but surely creating a balance. In just a few seconds, our 100 electrons have balanced out to 50 in the anode and 50 in the cathode. But oh no, what happened? The electric current has stopped flowing. Why did this happen? This happened because the amount of electrons is balanced, so everything is sitting happily right where it is. And since there is no longer an electron flow between the 2 points, the battery's cathode and anode lose their charge. They are now completely chargeless. This battery is now dead. Not that it had much charge anyway. It literally had 9.109 times 10 to the negative 30th grams of electrons. Yeah, that's 9,109 with 30 zeros before it. That's a very, very small number. So let's edit our circuit a bit. We'll recharge the anode so it has 100 electrons again, but this time we'll add a switch. Right now the switch is off, so no current can flow. This is because it is blocked by the insulating material built into the switch. If we turn the switch on, a bridge is made around the insulating material and an electron flow can exist. However, if we turn it off again, the flow will stop. So now we have a few new words for you to learn. You're probably familiar with them, however you may have been using them all wrong. I don't expect you to understand what the definitions mean, so I'm only going to have you focus on the symbols for them. A lowercase v stands for volts. A capital A stands for amperes or amps, and the Greek letter omega stands for ohms. I find this graphic much more useful than any of those definitions. Amps are the actual electrons traveling through the wire. The volt is the driving force. It defines how badly and with what force amps want to get from one spot to another. The resistance, which is measured in ohms, is trying to prevent the amps from getting to their destination. This graphic is also very useful to understanding this topic. In the leftmost graphic, we see that gravity is the equivalent of volts. It's pulling the water down and forcing it through the pipe. In the middle, we see resistance. In the open pipe, there is less resistance because the water flows evenly through it. In the smaller pipe, the water is clogged and has to flow in smaller amounts. And on the right-hand side, we see a demonstration of Ohm's law, which we'll go over in a second. Basically, we see that the smaller pipe allows less water or amps to flow. So now it's time to go over Ohm's law. What is Ohm's law? Well, Ohm's law is a definition to determine the voltage, current, or resistance of any electron flow. The V in this equation stands for voltage. The I, even though it doesn't really work that well, stands for current, and the R stands for resistance. We also have a very helpful tool called Ohm's triangle to work with. If we cover up the variable we want to solve for, we can tell which formula we must complete. If the variables are across from each other, you must multiply. If the variables are above or below each other, you must divide the top variable by the bottom. For example, if we cover up V, we see that we have to multiply I and R together. If we cover R, we must divide V by I. So let's try some practice problems. If we have 1 amp and 3 ohms of resistance, how many volts do we have? Well, let's plug it into our equation. Voltage equals current times resistance. So plug 1 in for the current and 3 in for the resistance. And this is what our equation should look like. So if we solve for this, we can see that we have 3 volts of electricity. Now let's try another. This one will be a little bit harder. If we have 50 volts of power and 10 ohms of resistance, how many amps do we have? So let's gather our data. 50 volts and 10 ohms. So that means we are solving for current. So let's cover up the I on our triangle. So now we know that we have to divide voltage by resistance, since V is on top of R. So our equation will be I equals V divided by R. Now let's plug in 50 volts into the V variable and 10 ohms into the R variable, and we see that our equation is I equals 50 volts divided by 10. Now we solve, and we see that our current is 5 amps. So how does this apply to electronics? Let's look at this LED for a moment. An LED is a light-emitting diode, which basically is just a little light bulb that doesn't burn out as frequently. This specific LED requires exactly 3 volts of electricity, and it seems like I only have a 9-volt battery. This specific battery produces 9 volts and 120 milliamps of power. So what happens if we connect them? Holy cow, our LED just caught on fire. But why did this happen? If we apply too much power to something, it will likely build up so much resistance that it either bursts into flames or fizzles out. This is why we must be careful when choosing components. So how do we fix this if a 9-volt battery is our only power source and we only have 3-volt LEDs? Let's grab a new LED while we think about this. So how can we solve this problem? It's simple. We just need to use Ohm's law to calculate the amount of resistance we need to lower the voltage of the electron flow. So let's grab our equation again. V equals I times R. We need 3 volts and the battery supplies 120 milliamps of power. So let's plug them into our equation. Our equation is now 3 volts equals 120 milliamps times R. Now, this equation only works if you're using amps, not milliamps. So we have to convert from milliamps to amps. 1 milliamp is 1/1000th of an amp, so 120 milliamps would be 1.2 amps. And since we're solving for R, we need to isolate it. Let's divide both sides by 0.12 amps, and we get 3 volts divided by 0.12 amps equals our resistance. So 3 divided by 0.12 is 25. So we need 25 ohms of resistance to make the voltage compatible with the LED. So how do we add resistance to a circuit? It's simple. We add a 25 ohm resistor. Now, if we connect the circuit, voila! We have our LED gleaming brightly, and more importantly, it's not on fire. There are a few devices used to change these different features in a circuit. Resistors are just one example, so let's take a look at them. Resistors, as we know, are used to set a certain amount of resistance to go through a circuit. Resistors are one of the most common elements in a circuit. On the right, we see what a resistor looks like. Resistors are very small and don't cost much, which is great. On a circuit schematic, resistors are usually represented by a zigzaggy line. Transformers change the voltage and amperage of a circuit. They are usually much larger than any other component, and they're often found when converting power from an outlet to something you would use with your smartphone or another electronic device. They are represented in schematics by a coiling or bumping line. 2 parallel lines in between represent an iron core, which improves the functionality of a transformer. Power sources come in all shapes and sizes. They provide the base voltage, amperage, and resistance for everything. They are key to any circuit. In fact, nothing powered by electricity can operate without one. Common examples are batteries, generators, solar panels, and turbines. So that wraps up our lesson today. I really hope that you were able to learn something new from this. If you have any questions about these topics, please leave a comment and I'll do my best to help you. If you enjoyed this video, please consider leaving a like, and if you'd like to get updates when I upload videos like these, please consider subscribing. Thank you all for watching, and I'll see you guys next week. Adios.